All right, welcome back for another episode of Connie 352. Today, we're going to be discussing domestic water pipe sizing. All right, we're going to size the supply pipe for the building. We're also going to calculate the total pressure loss to make sure that we have enough pressure to make the water closets work in a building, and then determine whether or not we need a booster pump for all of these things. So, pause here and get a couple of things. One, you need the plumbing handout. And then two, you need the Unit 3 plumbing systems, the plumbing systems packet. That will give us some examples and kind of help things out. So get both of those. And when you're ready, go ahead and hit the play button again. All right, let's take a look at page 244 of the packet, table 8.8. We've already looked at this. We looked at this when we did the wastewater sizing. So I'm going to go through these tables that we've already used fairly quickly. First things first, you find out how many people are in the building from table 8. Next, you go down to table 8.7 and you find out the total number of water closets that you need based on occupancy and based on activity. What is the building use group? What are they using it for? Remember, very frequently, you'll have a smaller number for the first 50 fixtures, and then after that, one fixture can handle up to 150 people in a theater or a church. And then for offices and schools and stuff, it's different. So take a look at that. So we get our total occupancy, then we get our total number of water fixtures. And then we go down to this table, table 8.6. Now, instead of using the drainage column on the left, we're going to be using the water column kind of in the middle. So see where it says load value and then water supply fixture units? That is the one that we're going to be using. Only use the total column. All right, this column there, it'd be the third column under water supply fixture units. We do not need to do the water separately from, we do not need to do the hot water separately from the cold water. So only use the total values when we're sizing the main for the building and then individual bathroom group sizes. All right, also don't forget, only use the public or general top half of this page instead of the bottom, which is private. Don't use that side of the page. All right. So we get the total number of water closets and lavatories and sinks and everything else. And then we multiply that by the total number of water supply fixture units. And once we add all that good stuff up, we're going to go down to table 8.3. Table 8.3 is a conversion table. It goes from water supply fixture units into the demand in gallons per minute. Remember, water supply fixture units aren't real units of measurement. They're kind of magical, mythical, nonsensical. They don't really they're not a real unit, but they are used to get the average flow rates that we can expect at different types of occupancies. Now, notice there is the first two columns. They start out with a really small number of water supply fixture units. And there is the column for predominantly flush tanks, and then the column for predominantly flush valves. In this class, we're going to be using this one, predominantly flush valves. Just cross off the flush tanks column altogether, because that's more for residential applications, and we're not going to be doing residential calculations. So we're only going to be using this middle one. If for some reason, and you shouldn't, but let's pretend you did, you had more than 1,000 water supply fixture units in your building, say for the final project, then you would use the third column, but you probably will not. If you get up to that many water supply fixture units, I don't know, let's evaluate what you're doing, okay? So let's use this middle one. And something important, this table is not linear. In other words, we can't just say, oh, look, 10 water supply fixture units is 27 gallons a minute and just use that as a ratio. That is not correct. This table is not linear. Now, what you can do, though, is let's say on your final project or something along those lines, maybe you do fall between like 80 and 100 water supply fixture units. What would you do there? Well, you can interpolate between two values. Okay, that's fine. That's not a large interpolation, and so it'd probably be valid. But just do that. Interpolate between water supply fixture unit values to get you your gallons per minute. Now, once we get gallons per minute, the next step is pipe sizing. Pipe sizing. Pipe sizing is on page 226. It is figure 8.6. Okay, figure 8.6. This is a Moody chart. And I hope everyone is familiar with it, or at least you should be, from fluids. This gives us the possible combinations of pipe size, fluid flow in gallons a minute, and friction loss in PSI per 100 feet of pipe. Proper way to use this is to understand the limitations. First off, the maximum velocity that we should have in a domestic water pipe is going to be 8 feet per second. 8. So find on your graph there. It's going from the top left to the bottom right. There's 10 feet per second, 8, 6, 5, 4, and so forth. For a buried underground water main, 8 feet per second velocity is just fine. If we were inside of the building and we were worried about noise in the pipes, I would probably use 6 feet per second. Like if it was above a classroom or maybe above an occupied space like an office or something along those lines, then you use this 6. But if it's either in a shaft, like an enclosed shaft that goes straight up through the center of the building, or if it was buried below grade, we would use 8 feet per second. So the proper way to use this table is to figure out your gallons per minute. Start here on the left side where it says flow rate. That's the part that we know, the gallons per minute, and then go across this table until you get to the maximum velocity line. Now, here's the thing. Very rarely is the maximum velocity line at that gallons per minute going to land right on a pipe size. See the 10, 8, 6, 5, 4, those lines going this way? Those are all pipe diameters. The way to do this is you find the smallest pipe diameter that lines up less than 8 feet per second if it's a buried water main, or 6 feet per second if it's above an office or a hallway. But you find the smallest pipe size that would fit. Now, a couple of caveats about this Moody chart. See that they've got pipe sizes that are like 5-inch pipe size and 3-inch pipe size and 3.5. Yes, those all exist, but they are very unusual. They are not standard pipe sizes that you would normally go purchase and install. However, since this is an academic exercise for a test coming soon to you, the right pipe size is the smallest one that still falls under that velocity limitation. All right, so let's say that we had 100 gallons per minute, something along those lines. 100 gallons per minute going through a buried underground main. You follow the 100 gallons a minute along until it gets to 8 feet per second. But then you will find right there at that intersection, you'll find that we're between 2-inch pipe size here below it and a 2.5-inch pipe size up above it. Well, we're not going to custom make a certain pipe size just because it's the ideal fit for your velocity and flow rate. You're going to purchase a real pipe size. So what you do is go back along this curve until you hit one of these diagonal pipe sizes. And what you will find is that a 2.5-inch pipe matches up with the 100 gallons per minute line right there. I'm going to put my arrow cursor on it. I hope you can see that. And that is your actual pipe size you're going to use. Yes, it's slightly oversized, but way cheaper than buying a custom one. So that is the point that we're going to monitor. And then you go down, follow this all the way down, straight down to the bottom. And that's where you will get the friction loss of PSI per 100 foot of pipe. In other words, if we had a 2.5 inch pipe at 100 gallons a minute, that lines up right about there. That would give us a 3 PSI per 100 foot pipe loss. So let's say that building, the edge of the building and the street are 100 feet away from each other. That would mean that we lost 3 PSI simply traveling into the building. Now, frequently, a designer might look at that and say, wow, that's too much pressure loss. I need something with less pressure loss. Maybe they would round up to a 3-inch pipe, or which would be back here, 3-inch pipe, 100 gallons a minute. That would be a 1 PSI loss. Maybe they might even go up to a 4-inch pipe. 4-inch pipe is fairly common. It might not be that much more expensive. If we go all the way back to a 4-inch pipe, that is a let's see here. Yeah, about a 0.3 PSI per 100 foot of pressure loss. So there's nothing wrong with oversizing it, especially if we do that to minimize the need of a booster pump. And that's going to be our next discussion is, well, how much pressure do we have versus how much do we need? And if we don't have enough, how do we change that? All right. So I hope everybody was following along. We're going to do an example here in a second. And then we're going to talk about pressure loss. Okay. As we're adding up the pressure loss for the building here, and now what I want you to do is switch to the examples. Okay. Switch to Unit 3 plumbing system. This is that handout. It is on Canvas. If you've never downloaded this, please do. And it kind of summarizes all of my lectures. So this is a good thing to follow. On the first page, see right here, where it tells you the design limitations, 8 feet per second for underground mains, 6 feet per second for branch risers, okay? And then it gives us water pressure calculation rules here right below that, and we'll look at an example here in a second. So what we're going to do is we're going to add up all of the pressure losses to get from the street, that's the city main, into your building, and then up to the most remote water closet to make sure that it can work. All right, now there is an example in the book, and then there's this example as well. A few things I want you to know right now. Pressure loss of the pipes within the building. That is, after it goes through the backflow preventer and it's in the building, we're going to just assume an allowance of 10 PSI maximum. Instead of trying to figure out every pipe size and elbow and T and fitting and loss as it goes throughout the building from the entrance to the water closet, that could be pretty time consuming, and in all honesty, it's kind of a guess until the building is built anyway. So let's just assume for this class that within the building that piping pressure loss is 10 PSI. Let's also assume, and the book uses this number as well, that a backflow preventer is 15 PSI as it comes into the building. Now, you might be asking, what is a backflow preventer? All right, these are all pictures of backflow preventers. They all accomplish the same thing. They're just for different sizes of pipe. What they do is they prevent water that has gone into the building from coming back into the city main. And the reason we would want to do that is that we need to avoid contaminated water that comes in. Maybe it's being used in a sink. Maybe there is a big tank at the top of the building with a hose in it. If suddenly the water pressure at the street was to go away for some reason, like a water main break, or maybe the building next door, they need to use the fire hydrant to fight a fire, that's going to cause a rapidly dropping pipe pressure in the main, and if your building is very high, your building might be the highest pressure around, so it might force water down and in to the city main. So the purpose of the backflow preventer is to stop that from happening. Code is going to require one of these at every building. Now, some of these are quite small. You see the guy holding this one, right? Some of these are quite large. See this one outside in warmer climates. Southern California, Florida, Texas, you might see these outside all over the place. It just saves space from having them on the inside of the building. But they are going to stop water from going back from the building into the municipal system. They also have a lot of pressure loss going across them. For this class, we're going to assume right here, okay, this line right here, the pressure loss from the backflow preventer is 15 psi. You may be able to find ones that are a lot lower pressure loss. In fact, you can. They do exist. But if I don't tell you, assume it's 15 psi, like on an exam or something. For your final project, if you need a lower pressure loss backflow preventer, you can use one. You just have to prove it by printing out a cut sheet from one of these backflow preventers. Watts Industrial, they make a lot of backflow preventers. That's where I would suggest that you start if you need a lower pressure loss backflow preventer. Same way with a meter. Every building service needs a water meter. Those typically range from 5 to 15 psi of pressure loss across them. If we don't say, then you use 15 psi. If you need it to be less, once again, say maybe for your final project, then you look it up and give me a cut sheet. All right, then pressure loss from the height of the building. 1 psi equals 2.31 feet. So what you would do is you would take the height of the building divided by 2.31, and that's the pressure loss that you would get to force water in and up to the top of the building. Typically, what I do is I just use the height of that building above grade, because you're going to be measuring, most likely, you're going to be measuring the water pressure at a fire hydrant that's at grade fairly close by. So I just use the total height of the building, and that would be a good value to use. And then down after that, this residual pressure at the fixture. In other words, we need somewhere between 25 and 30 psi at a water closet to make it work, to make that flush valve cycle. Let's use 25 because that's what's in your handout. Okay. Now, future allowance of 5 psi. That is a guess. It's a complete guess. Yes, you can include this, but unless you're certain an owner is going to want to have that, don't include the future allowance unless I would tell you differently, maybe on an exam. All right, so let's go over the pressure loss to go from a fire hydrant to the most remote water closet is the piping loss within the building, which is a 10 psi allowance, the pressure loss for the backflow preventer, which is 15 psi, the water meter pressure loss, which is another 15 psi. You have the height of the building that you divide by 2.31 to get from feet of head to pounds per square inch. There's the pressure loss across the fixture itself. And then we add all those up, and that's how much pressure that we would need. Okay. Here's a simple graphic. Now, notice on this page, I put 30 psi to make a flush valve operate. It depends on which flush valve. It could be easily be between 25 and 30 psi. So I put that on this graphic. Here's the water main. So right here is the connection at the street. And then to go from the street connection into the building, that is where you use the Moody chart and figure out your pressure loss per 100 feet and subtract off the pressure loss that way, right? And then once you get within the building, that's another 10 psi of distribution loss within the building itself. All right. And if we don't have enough pressure to make all of this work, we're going to have to purchase a booster pump. Next week, we're going to talk about the basics of pumps and piping systems. So stand by for the booster pump discussion. right? And let's get to the example. Okay. There is an example in your book, and then there's this one that I wrote out as well. So what we have to do, we figure here, is what is the total pressure loss or the total pressure to be available to make a water closet work without needing a booster pump. And here's the process. First off, you find the static height of the building. I listed it here on this example. It's 70 feet. So you divide that by 2.31 and you get a 30 psi loss just going from the ground to the top of the building, right? So we need 30 for the difference in height. The meter needs 15 psi. The backflow preventer needs 15 psi. Here's that piping allowance within the building. Here's the 25 psi minimum to get a water closet flush valve to work. This included the 5 psi of future allowance. That's optional. You don't need to do that. And then the friction loss here is the 5 psi at 100 feet, and it's 400 foot of entrance from this point to the building, and that gives you another 20 psi in loss. Now, notice that we only have 100 psi available to make this work. What can we do? If we went up a couple of pipe sizes, we could lower the loss. And probably what I would also do is drop this future allowance as well. Right? Maybe change the backflow preventer, maybe change the water meter if this was a final project. But there are ways to get down to the pressure that is available to make it work. You could also put a tank on there instead of a flush valve. Depending on the type of building, maybe you could use a flush tank and save a considerable amount of pressure as well. But what if you had a really, really tall building? All right, let's look at 801 Grand as an example. 801 Grand is 660 feet tall. That is 286 psi. No matter what we did with reduction in pressure loss for pipes or valves or backflow preventers or meters, you're never going to get there. So a building like 801 Grand would need a booster pump no matter what. And in fact, they might need to have a booster pump for the lower levels and then a second booster pump for the upper levels. Might even need 3 different lifts for a building of that high. So just keep in mind, some buildings, no matter what, are tall enough that no matter what you do, you will have to have a booster pump. All right. There is also an example in your book. Okay. If we go to, or in your book, in your handout, if we go to the handout, go to page 227, example 8.9, it kind of does the same thing and walks you through, right? The total water pressure required for a 70-foot high building, and then there's various things that you can subtract out. For the exam, use 25 psi for the water closet. All right, use 25 psi. In reality, it'd be nice to use 30 psi to make sure that it works, but we can use the 25 psi value in here. The one thing that I want you to do differently, you see where it says piping pressure loss on figure 8.8. If you go back to example 8.8, it breaks out entrance loss and internal friction loss and gives you an allowance to calculate for that internal friction loss. Don't do that. Do it the way I showed you, where we just have a 10 psi allowance for that internal, and then we do calculate the external pressure loss for the service into the building. All right. So for that example, if you add up all of those, they're 40 psi short. What that means is that we would have to have a booster pump and use a booster pump to make up the difference between what is available versus what is needed. All right. Now we've already done. We've already used this table here, table 811. That was for drainage fixture units. So here's what I would like you to do. Right? On Canvas, under modules, I listed plumbing homework 1, plumbing homework 2, and plumbing homework 3. I put all those on there. They give you a point total. However, in light of the current situation, we are not going to have you do the plumbing homework. Here's what I want you to do. I want you to make an honest attempt at it. Make an honest attempt at working out homework 1, 2, and 3. And then for the next time, I will probably record these lectures tomorrow. I'm not sure. They'll probably get posted up over the weekend. So what I want you to do is watch this video, do the homework that I assigned here, homework 1, 2, and 3. And then once you've made an attempt at it, I'm going to work out the answers on a video lecture next time. All right, so stand by for the workout, but I want you to try this on your own, and we're going to go from there. Okay? So look at the examples in this video, look at the examples in the book and in the text, look at all of them, see if you can figure out how to do these homeworks, and if not, I'll work them out next time. All right. Thanks for watching. Make sure you let me know if you have questions. We've only had a few people post questions to the discussion board, so make sure you ask them, and we'll go from there. Thanks, and see you all next time.